What happened to everyone? Okay, you all got to get here earlier. I told you guys too. You got to get here earlier. I wasn't kidding when I said pretty soon I'm going to start locking the door at 1:30. So, did everybody who was on the waiting list get in? Is there anybody still on the waiting list? All right, we've solved the problem. That's nice. So we're going to continue the nonparametric regression today. In particular, we'll finish up the kernel estimators. Any questions before I begin? Actually, maybe I should try it now. You're just in time because I was literally just going to lock the door. I'm going to try it and see what happens. It'll be very interesting. There. All right. I got to be here on time. So do you. All right. So let's remind ourselves what the kernel estimator is. So this is the form of the kernel estimator, just the local average of the y's. Remember, if we just call all of this the ith weight, oh, someone's trying to get in. The ith weight, should I let him in? Oh, you got to get here before I'm locking the door from now on at 1:30. I wasn't kidding. All right. Let's lock it. Next, and the next time I'm adding actually an electric charge. So you get a shock. So let's call all this the ith weight at the target point x. We got another one. And so the important thing is that it's a linear combination of the y's. Now the linear combination depends on the target point, but it is a linear combination of the y's. So you got to get here before I lock the door from now on. Yeah. There. This is called, in psychology, reinforcement training.
Reinforcement learning?
Reinforcement learning. Yeah, whatever it's called. I'm a statistician, I'm not a psychologist. Okay, so it's a linear combination of the y's, right? So that's important. This is going to be a common theme. In fact, here's an interesting thing. This is not in the notes until later, but I want to mention it now. We have this estimator of the regression function. Okay, it is defined, remember, not just at the training data. It's defined at all x's, right? However, it's interesting to examine its behavior at the training point. So suppose these are the training points. Let's look at that. So this is usually called the fitted values, y hat 1 up to y hat n. That just means that the regression estimator evaluated at x1, x2, xn. So let's look at what that is. Remember that the estimator is a linear combination of the data, the y's, but the linear combination depends on what point you're at. That's the kernel. So I'm writing it as an inner product here. We're taking y1 to yn is some linear combination of the y's. That's what gives me m hat of 1. Right? Now if I look at m hat at 2, so I have to move somewhere else, say 2 here. Of course, I'm changing the weights. So it's a different set of weights. I've shifted the kernel over, but still, it's a linear combination. This row times this column gives me m hat of 2. Okay? So what does that give me? Uh-oh. See, I told you I was going to lock the door at 1:30. Yeah, okay. So in matrix terms, y hat, that's the vector fitted values, is some matrix L times the data. That's the data vector. Does that look familiar? In linear regression, we had this very same equation. We had y hat was equal to the hat matrix times s. This was a projection matrix, right? An idempotent matrix that projected onto a lower subspace. Nonparametric regression has the same form. This is no longer, however, a projection matrix. In fact, it's called a smoothing matrix. But it's a linear smoother. Now, don't confuse, this is important, linear smoothers and linear regression. By a linear smoother, I mean it's a matrix operating on the data. So it's a linear operator. Okay? It doesn't mean that the function we're fitting is linear. But there is this really important connection here, is that there's a very similar thing going on in linear regression and in non-parametric regression. It's still a linear smoother. In fact, what we're going to see is many of the different non-parametric estimators you might know about. So reproducing kernel Hilbert spaces, Gaussian process smoothers, spline smoothers. They're all linear smoothers. They're all just different choices of the matrix L. In fact, here's an interesting thing. You can take any method you want for getting a non-parametric regression estimator, rewrite it this way, and if you plot this, each row, what you're going to see is how much weight it's putting on each observation. It doesn't matter what method you're going to start with, it's going to look like a kernel. So smoothing kernels are kind of a good way to think about these things, because even the estimators that start very differently, when you actually look at what it's doing to the data, it's behaving typically like some sort of kernel implicitly. So this is a good thing to keep in mind as we go through the notes. Okay, it's an example of a linear smoother. So we'll return to that point in some detail when we talk about different smoothers, but it's a good unifying view of many different non-parametric estimators. However, not all non-parametric estimators are linear smoothers. There are exceptions. If Ryan talks about what I think he's going to talk about in a week, he'll talk about a nonlinear smoother, for example. So many non-parametric estimators are linear smoothers, but not all. All right, so I had written down a key theorem which was the bias variance trade-off So this was on page 5. There was this complicated bias term, which, as we saw, had some undesirable features, like boundary bias and design bias. And then there was a variance term, which was 1 over nh times some other stuff here, and then lower order terms. So I want to outline the proof. The full proof is a little bit long, but I can outline the main idea. And then we're going to talk about the multivariate version of this, and then we're going to talk about local polynomial smoothers. All right, so this is still on page 5. So we're going to look at m hat minus m. Well, what you can see, did I erase the definition of the kernel smoother? Let me put it back. I've got a ratio of two sums. We know that it's easier usually to analyze averages, because averages converge to things. So I'm going to multiply the top and bottom by 1 over n. Okay, it doesn't change anything. And then I'm going to call the top, I think I called it a hat. Yeah, a hat of x. Does the bottom look familiar? Actually, let me also, well, I'll leave it out for now. But it's a kernel density estimator. Actually, you might notice the 1 over h is missing in front, but that's on the top and the bottom, so we can cancel that out if we want. But let's actually put that in too, since it's on the top and the bottom. And now you can see, this is just the kernel density estimator. Okay. So, all right. Oh, these guys are really late. Oh, you're late.
I'm late. I'm sorry.
All right. Where were we? All right, so we're going to rewrite this expression then, in terms of those quantities, a hat over p hat minus m. And the first thing we're going to do is just multiply and divide by something so that we get it into a more convenient form. So I would like to rewrite this as a hat p hat minus m. And now I'm going to multiply and divide by this quantity plus 1 minus this quantity. Might not seem like I'm accomplishing much, but the idea is I'm trying to get rid of the random denominator. See, we have what makes the analysis a little bit more complicated is that the denominator and the numerator are both random here. And so now, if I multiply this by this, and then this term by this, I'm going to get two terms. But the nice thing is this p hat kills this p hat, and I'm going to have a deterministic quantity. So what you get is two terms. After I simplify it, you just get this. Plus the next term. I've done a little bit of algebraic simplification here. Okay, so I really haven't done anything except rearrange terms. Now this is just going to be a proof outline. So the first thing to notice is that this is going to have some error. This is sort of what we're trying to analyze, right? This is something going to 0 at some rate. But this is also going to 0. So if we multiply two things that are going to 0, they're going to go to 0 even faster. Okay, so the dominant term is this term. This term is going to 0 faster than the original thing. So this is approximately equal to this. There's a little bit of hand waving there, but hopefully that's convincing. But the simplification now is that the denominator is deterministic instead of random. It's just going to simplify the analysis a bit. And so clearly, we need to analyze what's random here, a hat x and p hat x. Actually, p hat x we analyzed in 705. And a hat x is very similar. We can analyze it using very similar techniques. I don't want to, so remember, a hat x is that average. So the expected value of a hat x, well, the expected value of an average is just the same as taking the expected value of any one of them. So that's 1 over h times the expected value of yi, k, okay, and now I'm just going to write out the definition of expected value. It's just, well, actually, let's do two things. Remember, let's write yi is equal to m of xi plus epsilon I. So I can actually break this up into two pieces, the part with mi and epsilon I. But what's the mean of epsilon I? 0. So I can just stick in an mi here. And so I have m of xi, k of xi. What's random is the xi. So what I'm getting is the integral of m, let's call it u, times k of x minus u over h p of u. So if you remember how we analyzed the kernel density estimator, this was pretty much the same thing, except we didn't have this term.
Should that require that epsilon I is independent with xi?
No, not for the mean, but for the epsilon I always has mean 0, whether it's independent of xi or not.
But the expectation is epsilon I times the k xi. So how do you state this?
First, take the conditional expectation given x, and then uncondition. Okay. Do you remember what the trick was when we did this in density estimate? How did we analyze that? How did we put that into a form we could analyze? Change of variables, yeah. So you define, let's say, t equals x minus u over h. The Jacobian kills the h. And so you get m of x plus th, k of t, p of x plus th. Hopefully that rings a bell. Again, if it wasn't for this, it would be the same as the analysis we did for the kernel density estimator. And what was the next step we did in the kernel density estimator? We did a Taylor series expansion of this, right? P of x plus t, p prime of x plus h squared over 2, p double prime of x. And we do the same thing over here. And now, let me just explain what happens. I have 1, 2, 3 terms. I have to multiply them all out so you can see why it's a little bit messy. It's like 9 terms. But when I multiply by this, which is symmetric, any term, well, some terms are constant, like we'll just have an m of x out front, like an m of x, actually p of x somewhere. M of x times p of x. What happens when I multiply a term like this? M of x times this. But when I integrate that with respect to t, it's 0. Anything with an odd number of t's, t or t cubed, is 0 because of the symmetry. So you have to multiply them all out, integrate them. All the odd terms are 0. Anything with an h to the 4th is a lower order. And you get the expression at the top of page 6. That's how I got that expression. Then you have to subtract this term. But for this term, we do the same thing. We take the analysis we did for 705, where we had, which I think I wrote down for you to remind you that in 705, we showed that the expected value of p hat was p of h plus something of order h squared over 2 times p double prime times something I'm calling mu2, which is just the integral of, when you see a mu2 in the notes, it's just the second moment of the kernel. So if I take this times this times this, and I take what I just wrote out and subtract it, it's all just algebra. And that's why the expression, the final expression, ends up being so messy. But the important point I want to get across is now you can see, I wanted you to see where the m prime, why there's a first derivative there, why there's derivatives p prime. Remember we talked about the design bias p prime? I just wanted you to see where it's coming from. It's just coming from Taylor series approximation, multiply it out, integrate it, and we get stuck with all this extra stuff. Okay. So the important thing is the result, but I wanted you to have some sense for where these terms are all coming from. Okay. And the other thing I want to remind you about is there's an h to the 4th in front of the squared bias. That's coming from this analysis. There'll be h squareds around here. When you square it, you get h to the 4th. But that's only true because we're doing an interior point. If you did the whole thing at a boundary point, the Taylor series doesn't work out the same at a boundary point. And you end up with a bias at the boundary that's much larger, something like h squared. So I didn't include that analysis there. So the two key points, though, if I'm confusing you, because I know it's getting a little bit technical, but just look at equation 15 and just keep in mind the bias has two unpleasant properties. The presence of p prime says that anytime the density is irregular or unsmooth, you have extra bias. And then the part that I left out is anytime you're near a boundary, there's extra bias. And just so you know that this matters in practice, a lot of high-dimensional prediction makes use of the fact that something that we've noticed in the last 10 years, which is supposed to be helping us, which is that data don't tend in high dimensions often to be nice, uniformly spread out, right? If you've heard about manifold learning, you know that a lot of times data sets in high dimensions, they might be in very high dimensions, but they often tend to concentrate around lower dimensional sets. An example of that is, a famous example is you take a picture of someone's face and you have them move their head around. The number of pixels might be large, so the dimension of the space is very large. But really, if you follow the data in that space, it's only really moving around in a lower dimensional subspace. It might not be perfectly on a subspace, but the point is that the data, the distribution of the data in high dimensions, we shouldn't think of necessarily as being a nice smooth distribution. It might be something that's living on some really weird low dimensional sets. That's actually a good thing. It's something we take advantage of in statistics and machine learning. But what does it mean when the distribution is on some weird lower dimensional set? It means the density is very peaked. It means P prime is huge. So we're actually incurring a huge bias in our prediction error when it should be helping us. That's why that expression is important. All right, and so I'm going to tell you how to get rid of the bias in a few minutes. Before I do that, let me just say that Theorem 4, everything there was for one dimension. Theorem 4 is the same exact theorem for the d-dimensional case. I see a typo, though, that in Theorem 4, it should say the expected value of m hat minus m should be squared. I forgot to put the square. But that, you see, it's the same thing. You'll see there's a bias term, there's a variance term. It's just that now there's gradients instead of derivatives and stuff like that. And the proof is the same. It's just to use multivariate Taylor series instead of regular Taylor series. This is a nice example, I think, of how doing an analysis of some sort of learning algorithm gives you insight that you wouldn't naturally guess ahead of time.
So how does the dimension come into the picture?
So if we look at the dimension, let's look at the higher dimensional thing. What we see is that the bias is of order h to the fourth. So an interesting thing about the bias is never affected by dimension. But the variance term, I'm going to ignore constants here. So the variance term we saw in one dimension was 1 over n to the h. But if you look at the theorem here, it may be a little bit hard to parse, but in d dimensions it's this. That's where the dimension comes in the variance term. It's the variance that increases with dimension, not the bias. There's a bunch of, I've left out all those complicated, constants now.
Does the design bias change too?
Well, it involves the gradient of p instead of, so it'll depend how that density varies. So actually, we can ask now, what is the optimal bandwidth? Well, if we minimize that, you're going to get h to be of order, let's just write it like this, 1 over n to the 1 over 4 plus d. If I plug that back into the mean squared error, we're going to see that the mean squared error is of order 1 over n to the 4 over 4 plus d. So there's the cursive dimensionality going on. More generally, by the way, I kind of snuck some assumptions in there. There was second derivatives all over the place. So what kind of smoothness was I assuming? I was assuming second derivative smoothness. If I had redone the analysis assuming not just 2 derivatives, but suppose you assume there's 17 derivatives or something like that, you're going to get a different answer. You're going to always get what's going to start to look familiar to you is a rate like this, where beta you can think of as the Holder or Sobolev smoothness, but roughly speaking, it's how many derivatives, smooth derivatives we're assuming exist. So the typical case people do is beta equals to 2. That's the usual, for some reason, the most common case people work with, which would give us the 4 over 4 plus d. So there's two different things going on. There's the cursive dimensionality for sure. You can see the d there. We'll deal with that later to the degree that we can. But there's this extra thing nobody talks about, which is this design bias and boundary bias, which tends to get somewhat overlooked. That's not affecting the rate. It's affecting the constants. But it can actually matter a lot in practice. Okay? We haven't talked about the practical aspects of how to choose the bandwidth yet and so on. This is still just kind of an analysis of the basics of the kernel predictor. Okay, so before I go on, any questions then about the kernel predictor? Okay, the nice thing about it is I hope it's intuitive, right? You want to predict at a point, you're just taking a local average. In fact, computationally, that has advantages too. You can do lazy prediction. I don't ever have to compute this predictor. When you go to predict at a particular point, I just need to take the points nearby and take an average of those points. You don't need to store the whole predictor. And we have these results about the mean squared error, the bias, the variance, optimal bandwidth, optimal rate, and so on. And we're going to see later on in the course, when we do minimax analysis, that this is the minimax rate under the assumption of two smooth derivatives. If you assume m double prime exists and is smooth, you can't beat this rate. We're only going to try to improve the practical aspects now, not the rate. Okay? And we'll prove something about the minimaxity later on. All right, but let's now move on then to, is there a simple way to get a slightly better behaved estimator that still has this nice feature of being simple and based on the idea of local smoothing? So just to go back a bit, when people noticed these properties, there was quite a bit of research on how do we get rid of design bias, how do we get rid of boundary bias. People constructed some fairly complicated things until finally it was realized there's actually a very simple way to fix this. To see what that is, let's revisit where the kernel density, the kernel regression estimator even comes from in the first place. If I want to predict right here, say, give me a prediction right there. One way to think about it is we're just minimizing some sort of prediction error. If I asked you, well, suppose you had to pick a constant to do predictions no matter what x you were at, then what you might do is you might look at the error, the training error. I'll just leave that like that. Find a constant c which minimizes this. So what's the answer if I do that? Y bar. That would be the best predictor in some sense, but obviously that's constant over the whole range. If I want to localize it, if I want to say, no, I'm allowed to try to get a predictor that's specific to that local region, then you can think of kernelizing or putting a smoothing kernel that puts high weight at points where you're trying to predict. So now I'm letting the constant really depend on where we are, where we want to predict. We're localizing the training error. If you just take the derivative and set it equal to 0, you get exactly the kernel estimator. Just take the derivative, set it equal to 0, you get two sides, and so you get the kernel estimator back. So that's just another way to think about the kernel estimator. You're just minimizing the localized sums of squares. Thinking about it that way suggests an idea. What we're doing, we see, is we're trying to fit a constant everywhere. So at this point, I'm saying find a constant c that minimizes this localized sums of squares. Well, that suggests the following idea. Why fit a local constant? Why am I taking this to be a constant? Maybe what I should do is fit a local line. Or a local quadratic, whatever, a local polynomial. And that's what a local polynomial estimator is. So what we're going to do is instead of minimizing this, I'm going to take the kernel, and instead of subtracting off, I'll call it beta 0 now, just a constant and minimizing that, that's what we've been doing so far. We can also put a linear term, we could put a quadratic term. I'm just going to do this in one dimension for the moment, and I'm just going to go to the linear term for the moment. So all I'm doing is, in other words, least squares. I'm fitting a straight line, but I'm doing it locally. And if I do this, what's happening is you can think of my estimator in some neighborhood here. Let's pick a point near x. I'm saying that m hat of u, I'm going to say, is going to be beta hat 0 of x. Well, the way I've parameterized the line is that it's centered around x. So this is beta 1 hat of x times u minus x. That's just the equation for this line in a neighborhood u, for points u in a neighborhood of x. Okay, I'm just going to get out a line instead of a number. Where beta 0 and beta 1 hat come just by doing least squares, just by minimizing this. There is this kernel here, though, so it's not going to be quite the usual least squares. And that gives me a line. But of course, I'm only doing this to get an estimate at this point. So I'm really interested in this at x. And this part actually drops out. And we just get beta 0 x. So let me clarify something here. We're getting back just a single number. But it's not the same as fitting a constant. We're fitting a line, then we're pulling off the intercept of that line. That's just because we centered the line around x. That's not the same as just fitting a constant there. Okay, so you fit a local line, you get the line, now you evaluate the line at this point. That's your estimator. That's the local.
What do you mean by fitting the constant?
I mean getting.
C is dependent on x.
I'm saying if you fit this, you'll get the kernel estimator.
Yeah.
If you fit this, you're going to get a beta 0, beta 1 hat. The beta 0 hat is not equal to the c hat. The fact that you fit something else, the fact that you fit the beta 1 affects what you get out for the beta 0. Okay? But intuitively, it's just we're fitting a line, a local line, and we're taking the line at that point. And the amazing thing about this is this removes both the design bias and the boundary bias automatically. And let me actually write, and it's easy, by the way, because we're going to write down the exact solution. Let me write down what the estimator is. If we just write down the thing that we're minimizing in matrix form and minimize it, just take the derivative, we can write it out explicitly. So here's what you get. Let's say beta hat. Remember, it all depends on the point x you're predicting at. You get a different value at a different point. So this is beta hat. This is a vector. We only really care about the first thing, but the whole process still involves fitting both of these things. And the formula is, this is just a least squares thing. The only difference is the presence of the kernel. Now, I don't know if those of you who are taking regression, that there's ordinary least squares regression, but there's also weighted least squares regression. Who's taken weighted least squares regression? Oh, I bet you more of you have. You just don't want to say it. But anyway, if you do least squares and put weights in, you just get a modification of least squares. Why would you put weights in? Well, like for example, if some observations have a higher variance than other observations, sometimes you put weights in. In this case, the weights are coming from the kernel. Things farther away from the target point are getting lower weight. So what we get is what's called a weighted least squares solution. I'm going to put down the formula. It's x transpose w x inverse. So you can see there's going to be some matrix of weights. That comes from the localization. And then x transpose wy. Let me write out what these things are. So this looks exactly like an ordinary least squares estimator except for the weight matrix. And what are these matrices? Remember, we're not doing one least squares. We're doing this at every point x. So we're doing a whole series of these things. So this x, the design matrix in the regression is going to depend on the point x that we're at. Okay, so it's going to be 1, 1, 1, 1, 1, 1 for the intercept, and this is and the W is just a diagonal matrix with the kernel values. So this is just k of x minus x1 over h, and k, and then 0 elsewhere. This only comes from taking this equation here, writing it in matrix form, differentiating and setting equal to 0. That's it. And I'm just writing it in a very compact form. But you can see it's so simple that you can program it very easily. It's built into R. I would imagine it's built into MATLAB. I don't know. Maybe some of you know I don't do MATLAB, but it's certainly built into R in many packages. If I really wanted to be precise here, I guess I should put a sub x here, because this depends on the point x at which you're predicting. So this is not much harder than doing kernel regression. This is fairly quick. We're not going to prove those results, but it is true. I'm going to state the result in a minute, that it gets rid of all these undesirable properties without increasing the variance. And remember, after you've done this, your estimate is this. So at each point x, you form the corresponding x matrix, W matrix. You do least squares, you get this, and then you pull that off, and that's your predictor. Okay, there's a multivariate version. I guess I didn't write it down. Now, let me just state the key theorem, which we won't prove because it's quite involved. I should give you a reference. So there's a book called, I'm going to guess, Local Polynomial Estimation by Fan and this is a statistical approximation to the name. I don't know how to pronounce it. I don't know how to pronounce that name. I certainly don't know how to spell it. And I even asked Fan, how do you pronounce her name? He said, I don't know. His own co-author, he didn't know. But it's a very nice book. It has all the theory about local polynomial estimation. But the key is this. The local linear estimator has, here's the risk. And I already see a typo. No, well, I wrote it down actually in quite a bit of generality. I'm going to write, I allowed in the result that instead of picking a specific bandwidth, that you could have a whole matrix, capital H, of bandwidths. But nobody does that in practice. So let me write down what the result really looks like. It's this and times some constants. And then it's 1 over n h to the d, sigma of x over p of x, and some constants. So we see the same rate. This is the variance of y given x. And this is the density does appear in the variance, which is natural, because if the density is low, you don't have much data there, you'd expect the variance to be high. But the key thing is nowhere in this constant do we get that p prime term. There's no derivatives of the p. And it's also true that this formula holds at the boundaries as well. So we've cured the boundary bias and the design bias very simply. It's really a cool thing.
What about this P double prime?
Well, the p double prime is there, but that's true. I accept that there is a p double prime there, except for one thing. That's a typo. It should say m double prime. So if you look at equation 18, we expect the second derivative of the regression function to be there. So in equation 18, that's a typo. That should be m double prime. This should be your go-to predictor. It's an interesting thing that I would say in statistics. It probably is the go-to predictor, but probably not so much in ML. By go-to, I mean the first thing you try. It's easy. See if it works.
What's the intuitive explanation of design bias and boundary?
Well, you know the reason for the design bias. It came from the proof, right?
What's the word design mean?
Oh, why is it called design? The arrangement of the x's is sometimes called the design. So that's why we call the p prime of x design bias. It's probably not a good, maybe that's not a good term for it, but that's what it's called. And the intuitive explanation for the, by the way, for the boundary bias is this. Suppose you have data that looks like this. You're putting a kernel here, you're putting a kernel here, but what happens when you have data here? You're putting a kernel here, it's getting chopped off. You're losing the symmetry of the kernel at the boundaries. That's the intuitive explanation of the boundary bias. You can see this yourself. If you do a nice, just simulate some data that look like this. And if this is a good exercise to do. Then if this was a more applied class, I would tell you to do this. Fit a kernel estimator, you're going to get this. But if you fit a local linear estimator, you're going to get this. You will actually see the difference. Now, you might wonder, why did I stop at linear? Can you do local quadratic estimators, local cubic estimators, local quartic estimators? Yes, you can. So people will do local quadratic estimation in some cases for the following reason. There's another source of bias, which is at peaks and valleys. These estimators tend to underestimate peaks and overestimate minima. And if you really, most times that doesn't matter. Okay, that's not a big deal. But maybe you're doing a scientific application where you really want to get the peaks estimated well, then people would do a local quadratic estimator. Beyond that, I don't see much practical value in going beyond local quadratic. So people will usually use local linear, maybe local quadratic. That's about it. You do start to add variance once you go up to higher and higher terms. Okay, there's no free lunch. All right. So that's that one. Oh, and by the way, despite how we derived it, what do we have here? It's a local smoother. What did I say?
Local.
Sorry, linear, thank you. It's another example of a linear smoother. It's just a different smoothing matrix. Any questions then about local polynomial predictors? Actually, I think that's just like a random guy in the hallway. So there was. Did any of you know Andrew Moore? Well, you should know Andrew Moore. What am I talking about? He's the dean now. I forgot that he wasn't at Google anymore. Andrew was a very early adopter in machine learning, actually, of local linear predictors. So there is precedent in machine learning for doing local linear prediction. All right. Section 6 just repeats what I already explained, which is that what a linear smoother is and that many things are linear smoothers. I've already explained this to you. I do want to mention one thing about linear smoothers, which is something we'll find useful. Let's write down the equation again. Remember, linear regression is, you're going to have to, unlock yourself. Okay. Imagine if there was a fire and everybody got trapped in here because I locked the door, I'd be in big trouble. Linear regression, remember, looked like this. The predicted values are the hat matrix times y. Does anybody remember if I take the trace of the hat matrix, what I get?
P plus 1. P plus 1.
Right, the number, basically, let's call it D, the number of parameters we're estimating, the number of predictors. It's a measure of the complexity of the linear regression estimator. If you're fitting 10 regressors, you're going to get 10. So you'll see people, when we're doing linear smoothing, they'll take the trace of this matrix, and they'll call this the effective degrees of freedom. So like in a kernel smoother, one way to measure the complexity of your predictor is by the bandwidth. Smaller bandwidths are more complex. But another way people use is this effective degrees of freedom. You can check that this is always between 1 in n. And as the bandwidth, for example, gets smaller, the effective degrees of freedom increases. It's just another way to sort of summarize the complexity of your smoother. Okay, so you'll see that. I wanted to mention that because you will see that in the literature. All right, any question? Let's talk about another brand of predictors, penalized predictors or regularized, which would be to do the following thing. We're going to go yi minus plus lambda times some sort of penalty function, let's say j of m. Let's call it actually g. So remember, if I just minimize the training error, I'm just going to overfit the data. I'm just going to interpolate the data. The way we got to kernel smoothing and local polynomial smoothing was to localize the training error. But a different approach, probably one you're more familiar with if you've seen this before, is to add a penalty term where this measures in some sense the complexity of the thing, and then we want to minimize that. And there'll be a tuning parameter, which in some sense plays the role of like a bandwidth. It's going to control the complexity of the predictor. And so let me put down two that are commonly used. I'll just do the one-dimensional case for the moment. For many years in statistics, this was a very popular regularizer. G double prime. The idea being, if you try to overfit the data, G double prime is going to increase, so it's going to increase this term. So that's a penalty for complexity. Another one might be to use a reproducing kernel Hilbert space norm. That's reproducing kernel Hilbert space regression.
Is G an arbitrary function here?
Yeah, this is an arbitrary function. I'm going to minimize this over all G's. As you proved in the homework, that's a doable minimization. It's one of the questions in the homework, is to show you did it for the reproducing kernel Hilbert space. We'll come back to that in a minute. So this is a minimization you can actually do, even though in principle it's over infinitely many functions. In fact, this is a reproducing kernel Hilbert space thing for a particular reproducing kernel Hilbert space, it turns out. So actually, if you minimize this G with this penalty, what you get out is something called a cubic spline, which is just a piecewise cubic fit. So what ends up happening, say the data look like this, you get a, I'm going to draw lines here. The solution turns out to be some smooth function. I'm trying to draw it to look smooth. It's piecewise cubic, but also the first and second derivatives match here, so it makes it very smooth. And that's kind of popular in some circles. I'm not a big fan of the splines because it's as soon as you leave one dimension, it gets really messy to start talking about splines. But I have colleagues who like splines. I prefer local polynomial estimators. What does it look like? So I have a little discussion for you about splines, but let's actually talk about the let's suppose I take a reproducing kernel Hilbert space thing. Then what you proved or will prove, what day study Thursday, by tomorrow, you'll prove that the solution, it's not a very hard problem. So here's the fascinating thing about it is, I'm going to minimize this over all functions in this reproducing kernel Hilbert space. That's a very large space. And at first sight, it might seem like, how could you ever do that minimization? But what you'll see is that the solution ends up being of the following form. Let me use the same symbols. Yeah, alpha j hat. It's just a sum of kernels at the data points. That's the solution. And you'll see that the alpha hat this vector of alphas looks pretty much like a least squares kind of estimator. Actually, it's more like a ridge regression. It looks like this, where K is just the kernel, the matrix of kernel values. So the interesting thing about reproducing kernel Hilbert space regression is, despite the kind of abstract nature of the minimization problem, it's an infinite dimensional minimization, it turns out that the answer has a very simple form. It's just a finite sum of kernels centered at the data points, and the alphas come from essentially like what looks like a linear regression. And guess what? That should look familiar. Well, it's really the fitted values I should be doing that for, but it's a matrix times y. RKHS regression is another linear smoother. And if you plot the rows of the smoothing matrix, it'll look a lot like just ordinary smoothing kernels. So you can see there's a theme here, is that there's many different approaches to doing nonparametric prediction, but all roads lead to, well, not all roads, many roads lead to linear smoothers, and they're just different flavors of linear smoothers. Now, I'll tell you, I have a preference for local polynomial or smoothing kernel regression, but I know in the ML literature, reproducing kernel Hilbert space regression is probably more popular. Let me just, do whatever you want. You can use whatever methods you like, but I'll tell you why I think the RKHS approach has some disadvantages. So first of all, there's actually two parameters to pick. You have to pick this lambda, but the kernel, you have to pick a kernel, and people usually pick a Gaussian kernel is the most common choice. There's another parameter to pick. And the literature is fairly silent about how to pick both parameters and how they interact with each other. So it seems to me a little bit more difficult. Okay? It's not so easy to derive the bias and variance and all those properties of an RKHS estimator. It depends on the spectrum of these operators and all that stuff. It's much more complicated. But also, I think it's harder to understand what it's doing. To me, a kernel smoothing estimator is very simple. If I want to predict here, I take an average of the points around me. Averages are simple. If I say, no, I'm going to do this minimization subject to some constraint that a function lies in a reproducing kernel Hilbert space, it's a little bit hard intuitively to picture what it's doing. I think it's just harder to get a grasp of what that estimator is, at least for me. And then there's things like boundary bias, design bias. Nobody talks about that for RKH estimators, but it's there, and it's not obvious how to fix it. So, personally, I'm maybe have a very strong statistical bias here, but I find the kernel smoothers or local polynomial are easier to understand, easier to deal with. But in the end, frankly, there's probably not a lot of difference between these different methods because they all involve a tuning parameter that trades off bias and variance. And the really important thing is that you do that well. We'll talk about that when we talk about cross-validation. So if I use a local polynomial smoother and you use a reproducing kernel Hilbert space smoother, but we both carefully choose our tuning parameters, probably we're going to make pretty similar predictions. So in some sense, it's going to be, to some degree, a matter of taste and a matter of what's convenient for the problem that you're dealing with.
What about combining them together? Add a penalty and a local polynomial estimate.
You could do a localization and a penalty. That's an interesting idea. I've never thought of that. I'm not sure if there's any advantages to that, but that's an interesting idea. So far, everything we've talked about is a linear smoother. There are nonlinear smoothers. So just to give you a couple of examples, there are things called wavelet smoothers. These are nonlinear. There are things called trend filtering smoothers. These are nonlinear. So there do exist nonlinear smoothers. I don't want to give you the impression that they're all linear smoothers. Yeah. The most commonly used ones are linear. Yeah.
So with linear smoothers, what exactly does the linearity specify? Because we only tested at the training points. Right?
Yeah, it just refers to the fact that you can think of the smoother as a linear operator acting on the data.
But only when we're predicting what it is.
When you're predicting, right. That's correct. Yeah. All right. Any other questions? So section 8, I'm going to skip. It's just yet another thing. All section 8 says is you could just specify a basis ahead of time, like a Fourier basis, and regress on this basis. That's yet another way. I mean, there's a million ways to do this smoothing. I want to talk instead about cross-validation now, which is really important to all these methods. Let's check the time. Okay, we're good. So no matter what method you use, you're going to have to pick some sort of tuning parameter. It might be lambda in your regularized thing, or the bandwidth in the kernel smoother. And what we're going to do, of course, is try to choose that to balance the bias and the variance somehow. What we're interested in, I'm going to write it as a function of h. Let's assume we're doing kernel smoothing, and so there's a bandwidth h. You can put in any other tuning parameter there. And we'd kind of like to minimize some form of the training error. All we have access to is, of the true error. All we have access to is the training error. We know we can't minimize this. Right? What would happen if I chose the bandwidth to minimize this? What bandwidth would I get? 0, because then I could just make m hat equal to y, right? Just overfit it. It's the usual problem. So we usually use some version of cross-validation, and there's many, many different flavors of cross-validation. So one of the most common ones is leave one out, which looks like this. Let's write it down. To try to get rid of the bias from overfitting, I'm sure you've seen this before, I take out this pair xi, yi. And then I get my predictor, whatever predictor you're using. So I'll call that m hat sub minus I. And then we compare that to yi. All right, that's the usual leave one out measure of risk. Probably one of the more common methods. Here's a cool thing about all linear smoothers. You can compute this without ever having to leave one out. This is equal to, this is not an approximation, this is equal to 1 over yi minus the original fit divided by 1 minus, and that's the II term in the smoothing matrix. You're going to prove this on the next homework. It's very simple. This is an identity. So one nice thing about leave one out is that even though in principle you're doing it by leaving one out, you never actually have to do it. You can just use this identity. So you never have to refit the data, which is pretty cool. Okay, and that's exact. That's a common method. So what you're going to do is get now an estimated risk and choose the h, let's say h hat, which minimizes that. I actually don't know a lot of good theory for leave one out cross-validation, I have to say. This is an almost unbiased estimator of this, of the true risk. But the problem is they're all very highly correlated. So this is a high variance estimator of the risk. But it is easy and it is convenient. And certainly, I'm sure it's true in MATLAB too, but I know in R, most of the packages that do nonparametric regression, this will automatically do some version of cross-validation. Now there is an approximation to leave one out that simplifies things even further. What are these LIs? Remember, these are the diagonal things in that smoothing matrix, right? Suppose instead of putting L11, L22, I just take the average of these values. So I'm just going to take the average, and every time I see an LI, I'm just going to replace it with the average. Let's just suppose I do that. So what is the average? Well, what is this, actually? That's the trace. We called the trace the effective degrees of freedom, nu. What that does is I can now bring that out front. So now I have 1 over n. It doesn't depend on I anymore. So I'm going to get 1 minus nu. This is the Greek letter nu. I'm not writing it very well. And times the training error. Is everybody clear what I just did? I just took the individual diagonal terms, replaced them with their average. There's some asymptotic justification for that. But what I've done is simplify the formula. Now it's just a matter of taking the training error times this term. It turns out to be a little bit more stable. Because if one of these happens to get close to 1, this whole thing will blow up. Whereas this average quantity tends to be a little bit more stable. And it turns out in some types of regression, this is just easier to compute than this is. So that's got a funny name. That's called generalized cross-validation. It should be called approximate cross-validation. But it's called generalized cross-validation. So if you ever hear the term generalized cross-validation, think of it as an approximation to leave one out cross-validation. So when you run software, sometimes it'll spit out for you cross-validation. You better check which type it is. It might be leave one out cross-validation. It might be generalized cross-validation. And there's yet another version, okay, which is the following thing. Look at this term here. That's something like this. If I take this, if I do a Taylor series expansion of 1 over 1 minus x squared, that's approximately 1 plus 2x. So if I just do that here, I get yet another approximation to the leave one out, which turns out to be, I'm going to write it in this form. Where sigma squared, oddly enough, is just, again, the training error. Let me make sure I was clear what I did. I just took a Taylor series approximation to this, multiplied it out, and I get this term. Why would I do that? Does that look familiar to anybody? Certainly to those of you who have taken 707, it should look familiar. It's the training error plus a penalty term. You see the penalty is basically involving the effective degrees of freedom. This thing, how many of you have heard of CP? No? Okay. Well, anyway, there is this thing called the CP statistic that people often use in linear regression for choosing like how many variables to put in the regression. And it's this thing. It has a kind of intuitive feeling to it, which is just that you have the training error and you have a complexity term. And if you try to overfit, this will get small, but this will get big. The effective degrees of freedom will get bigger, and vice versa. But the genesis of it is really, it's an approximation to the generalized cross-validation. And the generalized cross-validation is an approximation to the leave one out cross-validation. So I've tried to kind of unify them all here, that you're going to see in various places people using these different versions of cross-validation, but they're really kind of morally the same thing. They're just all kind of different approximations to the same quantity. So if you haven't heard of CP, well, that doesn't help you. But some of you will come across CP, and it's just like an approximation to that expression. All right. So this is all still one flavor, really. These are sub-flavors, right? The flavor here is leave one out cross-validation. We haven't got to the other ones yet. And these are kind of sub-flavors of that flavor. I want to show you an example. Any questions so far? Here's a fun little example. I like this example just because it's tough. If you want to test something out, this is a good example, top of page 14. The function is known as the Doppler function. I'll try my best to draw it. It's a really hard function to estimate. Even for a one-dimensional problem, this is tough. And I generated some data. So I generated a point at random. Then I took the function and added noise, and I got a data set like on the right. What you see on the bottom left is the cross-validation score. And instead of plotting it versus, what kind of smoother did I use? I think I used a local linear regression. Instead of plotting it versus the bandwidth, I plotted it versus this effective degrees of freedom thing. You could do either one. And so you get this curve, and it's minimized around 166 effective degrees of freedom. So it's almost like saying I'm needing 166 parameters in this fit. That's pretty unusual for a one-dimensional fit, but this is a very, very complicated function. Look at the fit, though. I'm also using this to illustrate another point. Do you like that fitted function? I like it. Given the complexity of the function, I think they did a pretty good job. But what you do see is there's a compromise, which is it fits pretty well in the middle. At the right, I would say it's under-smoothing. And at the left, it's kind of over-smoothing. And that's because we're choosing a constant bandwidth. That's one of the things about linear smoothers, is they're homogeneous. This is a kind of example where a nonlinear smoother actually might work better. You might smooth less on the left and more on the right. But this is a pretty special case, right? This is a one-dimensional high signal-to-noise problem. Kind of thing that might come up in signal processing.
What is an example of a nonlinear smoother?
You really want an example of a nonlinear smoother? You'll get one. I'll tell Ryan to do nonlinear smoothers when he lectures next week.
How would this behave like outside the ranges?
You should never, good question. How does this behave outside the range? You should never extrapolate. One of the basic rules in statistics, you'll be excommunicated if you ever extrapolate beyond the data. I mean, it'll give you an answer, but don't trust it. Okay. All right, so this is all leave one out cross-validation. Probably a more familiar one to you is, or maybe more common, is like something like tenfold cross-validation. And that is, in my opinion, more reliable. Just to remind you how that works, you take the data, you divide it into chunks. People usually, use 5, 10, rule of thumb. And you take one chunk at a time. So you would leave out this chunk. You would fit your predictor. And now just get the prediction error on the chunk you left out and do that for each chunk. I'm sure you've all seen some version of this before. That gives you, again, if you average over all the chunks, now you get an estimate of the risk. That's a much more reliable estimate of the risk, it turns out. Well, that kind of makes sense, right? Because instead of using one point here, I'm using a big chunk of the data to estimate the risk. We'll talk about a theorem about that in a minute if we have time. This is something where we can actually theoretically say something about how well it's doing. So you might wonder, though, why do people use tenfold? I don't know there's any reason. I think that just sort of became a default. I actually did find a paper the other day about trying to find the optimal number of folds. It's like 60 pages long. It's very, very complicated. There's a million assumptions. The answer is the optimal number of folds, not surprisingly, depends on all kinds of things about the function that you'll never know. And so the final statement in the paper is, so go ahead and use 10 folds. Seems to work pretty good. So I think it's pretty hard to say general statements about what would be the optimal number of folds to use in k-fold cross-validation, unless you make a lot of assumptions. But in general, we're not going to know much about the function. But I do have a theorem here, which actually just does one fold. And a similar theorem would apply for 10-fold. But for simplicity, imagine we do the simplest version of this, which is simply that you train on 1/2. So you take half the data. And here I get m hat of h for a whole bunch of different values of h, let's say. I let h vary in some set of bandwidths. And now I just estimate the error on this half. So this is just a simplified version of 10-fold cross-validation. And now I get this error, and I pick h hat from there. Here's the question. How close do I come to the best bandwidth? There is some h which minimizes the prediction error. We just don't know what it is. This theorem here, theorem 11, says that the final estimator, I'll write it like this, actually. Oops. So this is just the distance of the final estimator with that bandwidth chosen by splitting compared to the truth is less than or equal to, and I put 2. It's actually a slightly smaller constant, but just to keep it simple, I put 2 here times, actually we don't need an expected value here. Well, actually we do need an expected value. Because this is going to be this is the estimator like you would choose if somebody told you this is the best possible bandwidth you could use, the one that minimizes the prediction error. And again, this constant can be made closer to 1. But what I want to get across here is 2 things. First of all, I'm going to have to choose and practice some finite set of tuning parameters, like a grid of tuning parameters. Luckily, that only comes in logarithmically, the size of that set. So that doesn't have a big effect on the error. What's really, really important about this is the hard part. This is n. What you're seeing here is the price you pay for doing cross-validation. The price for not knowing the best bandwidth. The price for estimating the risk is of order 1 over n. That's really important because that's smaller than 1 over n to the 2 beta over 2 beta plus d. Which is that's the statistical risk we're paying for trying to solve the statistics problem, the prediction problem. If this was of bigger order than that, that would tell you that trying to choose the tuning parameter is screwing up the whole problem. It's the dominant part of the problem. This result says it's not. It's of smaller order. It's very important. And here's a really interesting thing. When we do classification, it's not 1 over n. It's going to be 1 over root n. Regression is special. It's because of the quadratic loss function. So
the expectation was over the randomness in the training data?
Right.
What do you compare of this is the loss of what kind of I mean that do you compete how you compare this one? Why you said?
Oh, this is the best estimator in your class. We're trying to get as close as we can to the error of your best classifier. And I should have written this, by the way. This is actually 1 plus delta. And there's a constant here that depends on delta. It would have been clearer, probably.
So in this problem, we mean that there is only possible like finite number of h values.
Yeah, you can extend it actually to infinitely many, but it just changes the proof technique. But it doesn't matter because that's a smaller term. The key thing is the n.
But it's infinite, the right term actually.
Oh, and then you have to do different proof. Yeah, but it'll still be finite. That's not the bottleneck here. This is actually a remarkable result. Now, I didn't include the proof because it does use tools we've used, concentration and measure. But the proof, it's very long. It's a very, very long proof. Actually, let me give you a reference, if I can remember. I think I've referred to this. I think it's at the end of the notes, actually. Yes, the very last page, there's the first book, Gyorfi, Kohler, Kryzak, and Walk. The proof's in that book. Okay, and if you want to look at it, it's a Springer book, and on CMU you get Springer books for the PDFs for free now. So it's a great book. It's got so much stuff about the theory of regression in there. If you're interested in that stuff, it's a great book to download, and you'll see this theorem in there. But if you go through the proof, you'll see the proof it's long. It's not so difficult, but there is some concentration stuff. But we've done that stuff, so it's all stuff that, in some sense, is within the scope of the course. But the takeaway message is we're lucky. Cross-validation works. We can choose. We have a method of predicting, and we have a method of choosing tuning parameters. Okay. Any questions?
So you're saying that the k-fold cross-validation has this nice feature with respect to regression. What about just how does cross-validation do with respect to how to change with different loss functions?
No, so this is particular to regression. If once you get to different loss functions like classification, you may not get the same rate without additional assumptions. So what we're going to do next week is I want to tell you some practical ways to deal with high-dimensional problems, because in principle, any of these things, the RKHS predictor, kernel smoothing, local polynomial, there was nothing that said I couldn't apply it to any dimension. But you could have a lot of problems in high dimensions. And so I want to talk about some alternative ways of dealing with high dimensions on Tuesday. Then probably we'll start non-parametric classification. I'll put up some notes about that. And then, as I said, on Thursday, there'll be a guest lecture by Ryan Tibshirani. Any last questions? Oh, yeah.
Should we have started doing stuff for the project?
Yes, good question. The project. I think you have a project proposal due in 2 weeks, maybe? So should you have started? Yes. You should be thinking about what you want to do. Don't leave it. I know everybody ignores that advice. I do too. But don't leave it to the last minute, really. It's just what you should be doing is thinking about what possible topics might you be interested in and start looking around for papers, okay? All right, have a good weekend. I'll see you next. Is this Thursday? Yeah, I'll see you next week.